Hi everybody, this is Nageswara, Assistant Professor of Physics, Government Degree College, Chintalapudi. In this presentation, we will discuss about electric potential due to the spherical shell or also due to the spherical conductor. Before discussing about the question, we want to remember what is electric potential. We know the electric potential can be defined as an amount of work done to bring an unit positive charge from infinite distance to at a point in an electric field. So the electric potential V can be written as W by Q naught, where W is the work done on charge Q naught. We know the units of the electric potential is volt. And there is three cases we will observe to determine the electric potential due to the charged spherical shell. The first case is when the point P is outside the shell. Second case is the point P is on the surface of the shell. And third case is if the point P is inside of the spherical shell. In this first case, let us consider a spherical shell whose radius is capital R, that is represented by OC. A point P is lies outside the sphere or spherical shell at a distance r from the O, where we have to determine the electric potential. For this purpose, a charge q is distributed on the surface of the spherical shell. Because the spherical shell does not have any matter inside of the sphere. And also in case of spherical conductor also the charge is distributed only on the surface of the conductor. So in this case we have to determine electric potential at a point P. For this case we have to draw a line AP or CP. The distance of CP is taken as X. And also angle COP is equal to theta, and angle AOC is taken as d theta. To determine the electric potential, we divide the spherical shell into different rings. One of the ring is ABCD by two parallel rays ABCD. Because the potential at a point P directly cannot determine or cannot derive by the whole spherical shell. For this purpose, we have to divide the spherical shell into different circular strips. In this case, firstly, we have to calculate the potential at a point P due to this circular strip ABCD. Then this is applicable to the total spherical shell. Now, ABCD is a ring, circular ring having two planes AB and CD. And we know already CP is equal to taken as X and angle AOC is equal to d theta. This is d theta, and angle COP is equal to theta. From the right angle triangle OEC, where OEC, this is O, this is E, and this is C. From this right angle triangle, sine theta is equal to opposite CE by hypotenuse OC. From this, CE is equal to OC sine theta, that is equal to R sine theta, because OC is equal to radius of the spherical shell, that is R. And from the sector OAC, this is O, this is A, and this is C. From the sector OAC, we know arc AC is equal to radius into angle d theta. From this, AC is equal to R into d theta. Now, the circumference of the ring ABCD is how much? We know circumference of the circle is equal to 2 pi R. So that 2 pi into radius of the ABCD ring is CE. So that we know CE is equal to R sine theta. So that the circumference of the ring ABCD is equal to 2 pi R sine theta. Now area of the ring ABCD is equal to, we know, that is AC into circumference. That gives the area of the ring ABCD. We know AC is equal to R into d theta and the circumference 2 pi r sine theta. So that is equal to 2 pi into r square into sine theta d theta. That is the area of the ring. Now how much charge on this ABCD ring? We know if sigma is the surface charge density, the charge on the ring ABCD is equal to surface area into surface charge density. We know surface area is equal to 2 pi r square sin theta d theta into sigma is the surface charge density. But how much is the surface charge density? We know surface charge density can be defined as charge per unit surface area. That is equal to sigma is equal to q by surface area. So that sigma is equal to total charge q by total surface area 4 pi r square, where 4 pi r square is the surface area of the total sphere. Now when we substitute the surface area surface charge density sigma into the above equation, charge on the ring ABCD, that is dq is equal to 2 pi r square into sine theta d theta into q by 4 pi r square, where 2 pi cancel each other and 2 and 4 times 2 cancel each other, so that surface charge density of the ring ABCD dq is equal to sine theta d theta into q by 2. Now, what is the electric potential due to this ABCD ring? If we consider ABCD is a very small object, the electric potential due to the point charge V is equal to, we know, 1 by 4 pi epsilon naught into Q by R. When we use this formula to determine the potential at point P due to the ring ABCD, that is dV is equal to 1 by 4 pi epsilon naught into dq is the charge on the ABCD ring and dx is the distance between ring and P, that is x. But we know dq is equal to sine theta d theta into q by 2. When we substitute into that equation, that is electric potential due to ring ABCD is, that is dV is equal to 1 by 4 pi epsilon naught into sine theta d theta q by 2 by x, where there is two variables. One is theta is variable and second one is x is also variable. So we cannot integrate this equation to determine the total potential because there is two variables. So for this case, we have to change this equation into single variable. So how can? By taking the triangle OCP, that is x square is equal to capital R square minus small r square minus 2r cos theta according to the sine formula. When taking differentiation both sides, x is a variable, so the dx dx is equal to capital R is constant, small r is constant, so the remains constant, that is 0, and minus 2r into differentiation of cos theta is minus sin theta d theta, where minus minus cancel, so that dx 2x dx is equal to 2r sin theta d theta. From this, sin theta d theta is equal to x dx by r into r. When we substitute this value sin theta d theta into above equation, the potential dV is equal to 1 by 4 pi epsilon naught into q by 2r into 2 pi, that is x dx by r into r, where x is cancel each other. X is cancel each other, so that the potential dV is equal to 1 by 4 pi epsilon naught r cube by h by epsilon naught into 1 by capital R small r into dx. When we have to take integration of this equation, you can get the total potential V. The point P is outside, so the limits are, lower limit is small r minus capital R and higher limit is small r plus capital R. So by integrating the above equation, the total potential V is equal to integration dV, whose limit small r minus capital R minus r to small r plus capital R, that is equal to integration q by 8 pi epsilon naught into 1 by r into r dx, whose limits are r minus capital R to R plus capital R. Now the total potential V is equal to Q by 8 pi epsilon naught into 1 by R into R is constant, that is integration dx, whose limits are R minus R to R plus R. We know integration dx is equal to x. When we substitute the limits, 1 R plus R minus R, where small r and small r cancel each other. So capital R plus capital R is 2R. So and capital R and capital R is cancel each other, so that the potential due to the spherical shell at outside of the spherical shell V is equal to 1 by 4 pi epsilon naught into Q by R. So this equation, that is V is equal to 1 by 4 pi epsilon naught into Q by R, is same as the potential due to the point charge. So the total charge can be adjusted as the total charge is concentrated at the center of the spherical shell. So the potential due to the spherical shell at outside of the point is 1 by 4 pi epsilon naught into Q by cap small r. And what about the when the potential P is on the surface? On the surface is nothing but this is the point actually. At this case, small r is equal to capital R. So that the potential V is equal to 1 by 4 pi epsilon naught into Q by capital R. So the only difference is when small r is replaced by capital R, that is the electric potential on the surface of the spherical shell. Now if the point P is inside of the spherical shell, this is when the limit changes. At this case, the lower limit is capital R minus small r and higher limit is capital R plus small r. The limit changes. In the first case, small r minus capital R, lower limit, here capital R minus small r, because the distance, the charge, sphere having mass in between these and these places. Due to these limits, we can calculate the potential due to the charged shell. So that V is equal to Q by 8 pi epsilon naught into 1 by R into R integration dx, whose limits are capital R minus small r to capital R plus small r. So we know integration dx is x. So by applying the limits, that is r minus r to r plus r, where in this case capital R and capital R cancel, so that 2r is there. In case the two small r and small r is cancel each other, so that potential due to the spherical shell at inside of the inside is 1 by 4 pi epsilon naught into Q by R. When we observe the last two cases, the potential on the surface is 1 by epsilon 4 pi epsilon naught into Q by capital R, and inside of the spherical shell also 1 by 4 pi epsilon into Q by capital R. All these are constants. So the potential inside of the spherical shell remains constant. So graphically we can written like this. This is the spherical shell having radius capital R. Inside of the spherical shell, potential remains constant, does not change. And outside, if the distance R increases, the potential decreases like this. So this is the analysis of the electric potential due to the charged spherical shell or spherical conductor. Thank you.